Okay, so we're at the middle bullet now in our balance testing pipeline, the launch functions. So if you've got a database and it knows the names of your tests, maybe the tests themselves haven't been uploaded, but the way to run the tests is understood to the database, and the database knows something about your test results or what's going on for coverage. A small program can be made that will feed work into your LSF farm directly from the database. So it's not necessarily the case that people have to actively launch every job. Obviously, any job, any regression list that an engineer launches, that should take precedence. But when an engineer isn't launching a job, there's still plenty of useful simulation that can go on. For example, a test that hasn't been run in 2 or 3 months. Why not run it now? A test whose last run had a failing seed, or whose failing seed was run with a version of code and now new code has come on. Hey, maybe run that test again and see if it still fails with the new code. Because we've all done it. You run a regression, you'll get 100 errors, maybe 4 types of error. You might file at most 4 bug reports. You might debug at most 4 tests. You're not going to debug each of the 25 tests that have the same failing error. You're not going to necessarily include all those seeds in the bug report. But when the failure and the seed and the test name are captured in the database, the system can automatically rerun that test when the code revs to see if, okay, did that bug really go away? Is that bug really closed? Or was it just that the first error that we detected was masking some of these other errors? So a little bit of lights out execution there of tests is very useful. There's something like this in Wilson's presentation too about bug vice. The idea of automatically isolating a failure. So somebody makes a check-in and a test starts to fail. The tools like this can very easily do an n-ary search. Well, they'll run 10 snapshots of the code in parallel looking for where in time the test starts to fail. And you can, within 12 hours of nobody bothering to look at it, find the guilty party and chastise them viciously for having done a check-in without running a regression. So it's not all good news. If you have a program that's automatically sending jobs into your Linux farm, it can make you unpopular in the organization. And so there are a few things to consider. One is to look at time of day and to not necessarily send in lots and lots of jobs during daylight hours. Because even with an interactive queue, a 2-hour job can take up your machine. So depending on the size of the farm, that's less of a problem. Another is if you're running architectural simulations that are in an unlicensed language like C, there are some interesting fairness issues that just have to do with latency. A C-only job will grab a CPU immediately, whereas a job that requires a license will actually have a little bit of latency in getting the CPU. And during that moment of hesitation, the C job grabs the CPU. And so it can be really unfair, and the C jobs can take up the vast majority of a farm just because of that latency. So a little trick there is to have all your jobs wait for the same licenses. Then as soon as the job starts to run, you have it give up the licenses that it's not actually going to need. So storing coverage tables and coverage lists in database is the next thing that's very powerful. This is right between launching tests and processing results. And so a lot of how coverage is done, whether you're in System C, in the lab maybe with FPGAs where you can put in special registers to check for various types of coverage assertions, is with assertions. And so you can put assertions in C, you can put assertions in RTL. Did I say RTP? I'm sorry, that's supposed to say RTL. Yes, assertions are very popular in RTP. We have it on good authority. I'm sorry. In RTL or in the FPGAs. And so at the end of a simulation, the system can simply process what assertions fired and upload it to the database that, for this test, it's now seen this assertion. Or for this regression, we saw these assertions. Now, this can get out of control. And you need to figure out what information to store because it can grow. And so Wilson Snyder recommended recently one thing to do is to focus on the coverage assertions that haven't been hit that often. So over time, you stop storing and restoring the coverage assertions that are easy to hit and focus more on the ones that are a little bit more difficult to hit. So managing that is a big deal. But here's the thing. Now we're hitting critical mass. When you have your results, your coverage bins, and your test lists, when they are all data structures, there are some remarkable value improvements, productivity improvements that can be done. So, for example, very simple one, you can compute the expected time for a test list. How long does that test list take on average? Because you have the run times of how that test list is run in the past, how each test runs in the past. Even if it's run as part of a different list, you can know the amount of coverage expected in a test list. You know, okay, well, if you know the amount of coverage, you can start to optimize the amount of coverage. Imagine you take a test list and you sort the tests, the ones that touch the most assertions down to the ones that touch the least assertions. And then you start walking that list and you start noticing that, well, this test is completely eclipsed by the test before it, so you just get rid of it. Or you can start optimizing which tests take the longest. You can begin to optimize test lists to control how tight your fishing net is, how intense your coverage is, and trade that off for the time. You want a quick pre-regression check-in that's got just the right amount of coverage, you can start to do those things. In addition, you can start to manage the life cycle of a test. And this is another thing we were talking to Paul about a couple weeks ago. Tests have a prime of life. When a test is created, it's more likely to find bugs than a year later. Now, tests are always useful in finding bugs and regressions, and no test should ever be thrown out completely, but does it have to be in your nightly regression? Maybe a new test that has similar coverage characteristics ought to be in your nightly regression. So this is a situation where when you can start to manage your test list and on a daily or weekly basis optimize the value that you're getting out of your regressions, you can actually reverse the typical trend. The typical trend is as you approach the end of a testing phase, your testing becomes less and less productive, less and less useful. There's more and more dead weight in your test list. You're less confident that any one test is going to find a bug. Whereas if you're analyzing the tests and constantly trying to swap out tests that aren't finding bugs for tests that are, or constantly being sure that you're running a test that hasn't been run in a while because you've got that information of when it was last run, then that's when you're really getting those productivity improvements that we're looking for. So then, checkers. Obviously, if you're going to run 100 tests a day per person, 1,000 tests a day per team, you're going to need automated checking. People can't dig through these results. But an important lesson with automated checking is not to let it define your testing strategy. So when a given automated checker, take something that checks QoS correctness or QoS behavioral requirements, if you're only creating tests that will pass that QoS checker, if you're only sending in valid QoS input, then you're restricting your testing. And so the environment needs to be created so that a test is only meant to pass on one type of checker. And you want multiple types of checkers. So you're cross-firing across your design. You run as many tests as you want, but don't get tunnel vision on one type of checking such that it limits your testing population. So creating multiple testing languages is one way to go about this, because even within a testing language is only meant to touch certain things. So like take the command line interface that I was talking about earlier. It's great for configuring how the queuing is going to be set up in a router. It's not so good for saying what two events are going to happen at the same time somewhere. So an environment should be as diverse and agile as possible. There should be as many ways to stimulate the design as possible. That diversity is going to bear more fruit than 10 degrees of complexity on a single channel testing method. And so finally, leveraging open source pieces, but the right open source pieces. So there are lots of open source databases that can be leveraged to store your information. And there are lots of open source packages that can be used to help you upload and download your information, to parse things, and to visualize your data. But it needs to be flexible and easy to use. So the web viewing, so just a quick question here. How many people are using web pages to look at regression outputs, testing outputs? Oh, wow. So that looked like it was almost half the audience. Maybe it's only a third, but that's great. So you use these web packages that'll help you upload your results to the web and help the whole team stay in sync. You can drill down. So the nice ability with a lot of these methodologies is to be able to start looking for one thing, but then pivot and look for something else. So I have a failing test. Okay, well, has that test failed before? Okay, I see. It failed back then. What happened just before that failure? What happened just before this failure? Was a similar file touched? These are the types of techniques that people are employing right now at that we're talking to get their verification effort done. There's a concept of status too. When the tool is capturing what's on, what's passing, what's failing, you can begin to get more insight on the quality of metrics. So for example, for bug tracking, we'll often use bug tracking to know when a project is ramping down, when fewer bugs are being filed, and when the code is more stable, then you know that a project is getting closer to completion. But there are other metrics to be looked at, like how many tests are being run, and if there are more tests passing than there were. Are there more tests being created than there were? Are there fewer tests being run with waves turned on, fewer seeds being replicated, all which imply debug operations? And so being able to visualize the status of the project through a web interface is very important and can help keep a large team, especially a multi-site team, in sync. As we talked about in the multiple levels of testing, we've got architectural testing, RTL testing, and perhaps lab testing or emulation going on in parallel, to be able to keep your tracking separate for those. So you're going to mirror your results database, maybe your test database, for those different models simultaneously, so that you can be sure that the coverage you're getting in one model is being approximated in another model, and that all of your phases that are going on in parallel are drawing to close at a similar clip. And so in the project that I had worked on, ending in 2006, we had adapted an open source database management website as our principal interface to look at what was going on in our regression farm. And it was great because it satisfied 80% of our needs out of the box. But it was a particular coding style, and it was somewhat difficult to maintain, and only a few people ended up leveraging it. In addition, it was very SQL focused because it was a database management package to start with, and not as many members of the team learned SQL as had initially said that they might be interested in it. So, I would strongly encourage you to not expect the team to learn SQL. So get something in place that will help get this leverage on your environment, help get these productivity gains, but not expect too much of the user. So finally, in conclusion,